Hello, everyone. Let's solve some system of linear equations using the Gauss-Jordan elimination algorithm. Let's go. Let's use the Gauss-Jordan algorithm to solve this first example. Here we have three equations with three unknowns. So the first thing that you do when you want to solve a system of linear equation is you associate its augmented matrix. So here, if you read the coefficients for A, you get 1x, 1y, 1z for the first equation, minus 1x, 0y, and 2z for the second one, and you get 2x plus 3y plus 1z for the last equation. And then for the augmented part, if you look at the constant terms, we have 6, 5, and 11. So now that we have our matrix, the goal is to put this matrix in a whole reduced echelon form. Right now, of course, this matrix is not in echelon form. In the first column, we have leading coefficients everywhere. So I know my first pivot is going to be on the first row, first column. And what I need to do is perform two elimination to get rid of the -1 and the 2 below. So what are these operations? So to get rid of -1, I'm going to say that row 2 becomes row 2 plus row 1, because -1 plus 1 will just go to 0. And then how do you get rid of 2? So here, if you look at row 3, the way you're going to get rid of row 3, and here I'm using that pivot as the eliminator. I have a 1. This example is perfect. So here, if I want to remove that 2 in the third equation, I'm going to remove 2 times row 1. So it's going to be row 3 minus 2 times row 1. So when I'm doing my operations, any row that is untouched, like in this case, the first row, I can write it quickly but carefully. So 1, 1, 1, 6 is untouched. I know my first element is going to be my future pivot. And of course, under that pivot, I'm going to get 0. That was the point of those elimination. If you're not getting zeros, something is wrong. But the tricky part, the part where you have to be careful, is you need to carry that operation throughout the row. So yes, -1 plus 1 is 0, but then you need to continue. So on the second column, 0 plus 1 will become 1, 2 plus 1 will become 3, 5 plus 6 will become 11, and that's your new row 2. And then again for the last row, so of course 2 times, so 2 minus 2 times 1 is 0, that was the point. But then you continue, 3 minus 2 times 1, you're getting a 1. 1 minus 2 times 1, you're going to get -1. And 11 minus 2 times 6, you're going to get -1 again. So that's my next matrix, and now I have to continue. So to some extent, for now, I'm going to ignore the first row and just focus on finding a pivot on the second row by looking at the first column with non-zero entry. And here I can see that the first column with non-zero entry is 1, 1. And I'm lucky here. What a coincidence for that example. My entry in the second column, second row is a 1. So it's going to be like perfect for elimination. So what I need to do now is I want to make sure that there's no leading coefficient under it. So I need to do another elimination. So here I'm going to transform my row 3. So row 3 will become row 3 minus row 2. Here it's important to use row 2 because if you're using row 1, you're going to be even if this is going to cancel that one, it's going to be reintroducing an entry in the first column, and you don't want that. So that's why I'm putting that wave thing, like I'm not using row 1 because this would undo my work. So here, since I'm not changing my first row, I'm going to rewrite the first row quickly but carefully. So 1, 1, 1, 6. I'm also not changing row 2, so 0, 1, 3, 11. Now I'm doing my operation, and here you can see in the first column I'm playing with zeros, so nothing is changing. Even if I go 0 minus 0, nothing is changing. But in the second column, the point of that elimination is 1 minus 1 is 0, and then -1 minus 3, that's -4, and -1 minus 11 for the augmented part gives me a nice -12. And actually at this point, so just a small remark here, I'm always going to force you to go all the way to whole reduced echelon form. But at this point, this matrix is in echelon form. So at this point, we could already comment on the type of general solution that we have. So if we look at the A part, so the coefficient part, and we count the number of pivots, we know that there's 3 pivots, so the rank of A is 3. If I look at the full matrix, because there's no pivot in the extra column, the rank is also 3 when I look at all 4 columns. And here the number of variable, we have x, y, and z is 3. When all these numbers are equal, so all of those numbers are equal, we know we're going to get a unique solution. So you can already predict what's going to happen with this system. And to some extent, you could, like if you read the third row here, we have minus 4z is equal to minus 12. You could compute z, then use backward substitution to compute y and then x. But because I'm going to always ask you to put that augmented matrix in row reduced echelon form, I'm going to continue. So my next move is to make sure that all these pivot to go from echelon form to row reduced echelon form. I want all these pivots to be equal to 1. Here already 2 of them are 1, but the last one is minus 4. So I can rescale that last row. So if I look at row 3, and I multiply it by minus 1 over 4, if you're dividing by 4 everywhere, I'm doing a rescaling, that will create the one that I want. So here I'm not touching the first row. So here we go again. So you write your first row, 1, 1, 1, 6. You're not changing your second row. So 0, 1, 3, and 11. And then the last row, rescale 0, 0, 1. And then when you take minus 12 divided by minus 4, you get 3. Now all my pivots are indeed equal to 1, but they're not alone in their respective column. So the Gaussian algorithm is you do elimination to destroy shit under. So pivot by pivot from left to right, you destroy the entries under the pivots. But for row reduced echelon form, once all your pivots are equal to 1, you destroy over from right to left. Actually, here that right to left is more of a choice, but in terms of efficiency or in terms of number of operations, it's going to be a lot easier if you do it that way. So I'm going to do 2 eliminations here to get rid of the 1 and the 3 above that 1. So row 1, so if I want to get rid of row 1 here, the 1 in row 1, I'm going to say row 1 will become row 1 minus row 3. So remember, I'm using the pivot as the eliminator here. And then for row 2, I want to get rid of a 3. I'm going to say that row 2 is row 2 minus 3 times row 3. So here the only row unchanged is row 3. So I'm going to rewrite that row quickly but carefully. Of course, on top of that one, I'm going to get zeros. So the one that I'm focusing on right now, I'm going to get zeros. Those were the points of my eliminations. And now what I'm going to do is also rewrite the first 2 columns because I have zeros, and that's the point of going from right to left. Because I have zeros in the third row, I know that my first 2 columns are not going to change. So I can rewrite the 1, the 1, the 0, and the 1 because I'm playing with zeros, so I'm not changing anything. So the true computations in this case are only happening in the augmented part. So if you take 11 minus 3 times 3, you're going to get 11 minus 9, which will give you a clean 2. And then 6 minus 3 is going to be giving you a nice 3. Now I'm almost done. So now if I move to my next pivot in the second column, I need one more elimination to have this matrix in row reduced echelon form. So to get rid of that one on top of the second pivot in the first row, I'm going to say, well, row 1 will become row 1 minus row 2. So I'm not changing the second row and the third one. So I'm going to rewrite those 2 rows quickly but carefully. So 0, 1, 0, 2, and then 0, 0, 1, 3. And then I'm going to do my operation. So 1 minus 0, of course, I'm getting a 1. 1 minus 1, of course, I'm getting a 0. That was the point of that elimination. 0 minus 0, a lot of action here. And then 3 minus 2, you're getting a clean 1. And now, my friends, all our pivots are equal to 1. All our pivots are alone in their respective column. That matrix right here is in a row reduce echelon form. So that's the ultimate state of that augmented matrix. And now I can read the solution. I already know it's a unique solution, but I'm going to extract it from that matrix. So remember at the end, what I like to do, I like to label my rows as equations. I also like to write the variables in their respective coefficient columns so to really help you read what's going on. So when I look at the first equation, so the first equation here, when I read it, you need to be very comfortable with this. Reading a row or an equation, it's the same thing. So the first equation is x equal to 1. Well, 1x plus 0y plus 0z equal to 1. So just x equal 1. What's the second equation here? It's 0x plus 1y plus 0z is equal to 2. And then the last equation is 0x plus 0y plus 1z is equal to 3. So we're getting our unique solution. So in canonical form, we have x, y, and z is equal to 1, 2, 3. And as remarked earlier, we have a unique solution. So in this system of linear equation, only 1, 2, 3 is a triplet that fits in that system. There is no other. So that's my unique solution. All right, that's it for that example. For our next example, we have again a system of linear equations with 3 unknowns and 3 equations. So the first thing, as usual, always you have a system, give me the augmented matrix. So 1x, 1y, 1z equal to 1, 2x, 3y, 3z equal to 3, 4x, 6y plus 6z is equal to 8. I have my augmented matrix. And now again, this matrix, and this is going to be classic, that matrix is not in echelon form. We have leading coefficients all in the first column. We need to do some elimination. So here I have already a 1 in the first row. That's perfect. That makes my life easier. So I'm going to eliminate the 2 and the 4 under it by using 2 eliminations. So my first elimination is row 2 becomes row 2 minus 2 times row 1. That will clear that 2. And row 3 will become row 3 minus 4 times row 1. So I'm not changing my first row, so I can rewrite that first row quickly but carefully. So of course I'm going to get zeros under my first pivot because that was the goal or the point of doing those 2 elimination, but I have to carry out that operation. So 2 minus 2 times 1, of course I got my 0, but 3 minus 2 times 1 will give me a 1. Again, 3 minus 2 times 1, 3 minus 2 times 1, I get a bunch of 1s. That's perfect for me. And then same thing for the last row now. So 4, of course, 4 minus 4 times 1, that gives me my 0. But then I continue. 6 minus 2 times 1 minus 4 times 1, sorry, will give me a 2. 6 minus 4 times 1 will give me a 2 again. And 8 minus 4 times 1 will give me a 4. Here we go. So now again, I like to ignore my first row. I'm done with my first row. I have a pivot, first row, first column. You will always have a pivot, first row, first column in every single question. Now the first row, ignoring the first column, ignoring the first row with known 0 entry, is the 1, 2 in the second column. And I have, again here, a nice 1 placed in the right spot. My life is easier for sure. So I'm doing my elimination to get rid of that 2. The way you're going to get rid of that 2 is by saying row 3 will become row 3 minus 2 times row 2. Again, I'm using row 2 because if I use row 1, I would undo my work. So here, quickly but carefully, I can rewrite my first row, 1, 1, 1, 1. And my second row also, 0, 1, 1, 1. And now I do my operation. Of course, 0 minus 2 times 0, nothing happens. Of course, again, 2 minus 2 times 1 will give me 0. That was the point of that elimination. Same result for this one. So very efficient with my elimination here. And then 4 minus 2 times 1 will give me a nice 2. Oh, that's interesting because I have my leading coefficient in the first column for my first row. The leading coefficient in the second row is in the second column, but the leading coefficient of the last row is in the augmented part. So that matrix is in echelon form. So we can actually talk about the type of solution that we have. What is the rank of A? Well, there's 2 pivots in A, so the rank is 2. But if I compute the full rank of the augmented matrix, I get 3. As soon as those two numbers are not equal, we know that there's no solution. Again, here, the best way to describe that there's no solution is if you read the last equation here, this is 0x plus 0y plus 0z is equal to 2. There's no triplet in life that will be such that when you multiply all of them by 0, that they will resurrect into a 2. So there's no solution of that system. As soon as you have a pivot in the last column, there's no solution. But because I will always force you for long questions to write the matrix in row reduced echelon form, that matrix is not in row reduced echelon form. Not all my pivots are equal to 1, so I'm going to continue because I like to torture you. So here we go. So I want to get rid of that 2, so I'm going to rescale it. So row 3 will be simply rescaled by multiplying it by 1/2 or dividing every entry by 2. So again here, quickly but carefully, I can rewrite my first row, my second row, untouched, and then I'm rescaling. So by dividing by 2 everywhere, now every single pivots are equal to 1, but that's not enough. I need to destroy the entries on top of each one of them, starting with the rightmost pivot. So I want to do elimination to get rid of those 2 ones, but things are not too difficult here. So row 1 will simply be row 1 minus row 3. That will get rid of that 1, and then row 2 will be also row 2 minus row 3. Remember, I'm using my pivot as the eliminator here. So the only row unchanged is the third one. So I can rewrite that row quickly but carefully. And of course, I chose operations that gave me zeros on top of that one. But because of all those zeros in the third row, using that row, and this is why you go from right to left, there's so many zeros in the bottom rows that there's not a lot of operation. Actually, here, nothing changes in the first 3 columns for row 1 or row 2 because of all those zeros. So it really makes these computations slightly simpler. Now one more elimination. So there's only one pivot that is not alone, and it's the middle one. So one more elimination here. So row 2 will become row 2 minus row, not row 2. So you see here, I'm the worst teacher. Here we go. So row 1 will become row 1 minus row 2. So that will get rid of that 1 here. So again, like when I do these things, I like to rewrite all the rows that are not changing. So row 2 is not changing. So I like to rewrite that row quickly but carefully. Row 3 is not changing. So I like to rewrite that row quickly but carefully. And then I do my operation 1 minus 0, 1 minus 1, 1 minus 1, 0 minus 0. And now here we go. Now we have a nice matrix in echelon form where all the pivots are 1, all the pivots are alone in their respective column. That's in the whole reduce echelon form. Oh yeah. So I'm very happy. Of course, it's not changing the fact that we already knew our fat conclusion that this system has no solution. We knew this from the echelon form. But if the question is to construct the whole reduced echelon form, you need to go and finish that question. And this includes the last column. I would say this is a common mistake. People not putting the last column, like not dealing with a pivot in the last column, thinking that, it's in the last column, I don't care. No, like all the pivots, including the one in the augmented part for the whole reduced echelon form, they need to be one, they need to be alone in their respective column. All right, so for that example, that's it. So for this video, that's it. That's all. Bye bye.